All right, boys, we started this problem at the end of class, and I want to finish it up right now. Recall we're thinking about different ways to express points in a plane, and we went through polar points and polar equations, and now we're given a little different look, parametric equations. And so these parametric equations, and we're looking at one of them that we discussed at the end of class today, just use a third variable, in this case t, it's almost always t. We call that the parameter to define x and y, right? So it has its advantages. It also has parametric equations, some disadvantages. But we've been talking about how we can kind of think about graphs of parametric equations, how they have direction, how we can establish different moments in time, where that particular parametric equation is, and some of the benefits of using this sort of thing, usually within the context of physics. But let's take a look at this one we ended with today, but didn't have a chance to finish. So here we have x and y, both defined as two sine and cosine containing functions, both of t. And so let's use Desmos to kind of think about what that might look like before, rather than graphing my hand, before we actually convert to rectangular, or what we call eliminate the parameter. So the way we use Desmos to graph parametric equations is we kind of think about a point xy. In this case, a point x is 2 plus 2 cosine t, comma, and the y value of any point is going to be 2 plus 4 sine t. Just the one on the board that we started at the end of class, but didn't have a chance to finish. So, there it is. It's a nice little ellipse, stretched out circle. And again, one of the benefits of parametric equations is it allows us to define a range of t of the parameter. And so if we, for some reason, only wanted half of that, we can go 0 to pi, or if we, for some reason, want a quarter of that, what looks like an ellipse, and it is, we can go 0 to pi over 2. And based on this particular range of the parameter, we can also get a direction. Okay? And so we're going to skip right to the eliminating the parameter piece, but that clearly is an ellipse oval. But remember, an ellipse has a major and a minor axis. It looks like the minor axis is x on the x-axis, the major axis along the y-axis. In the center, it looks like it's around here. Right? So let's see if we can derive the equation of this ellipse that we're looking at. However, for now, it's defined in parametric equation. So let's go back to the algebraic piece of this. We want to eliminate the parameter and express this in terms of a rectangular relationship. In this case, it will probably be an ellipse, and it is. So here's what I think we should do. Let's, we want to almost always, when we're dealing with sines and cosines, we want to end up using this nice Pythagorean identity. All right, that's one way to get rid of or eliminate, in this case, a parameter t, which is caught up with the cosine of t and the x, and the sine of t and the y. So we have to create an opportunity to build that and then substitute. So as we have done in the past, let's square both sides. But before we do, it would probably be easier to, in the x parameter, subtract 2 from both sides. And do the same thing in the y parameter, subtract 2 from both sides. Right. Now that's going to give us a little bit easier opportunity to square both sides. So that means x minus 2 squared will be 2 cosine t squared, which ends up being 4 cosine squared t, to square both sides. And we'll do the same thing with a y minus 2. Square that side. And I'm going to square 4 sine t, which is 16 sine squared t. Okay. Now again, I can see the cosine squared and the sine squared t kind of coming to life in this parametric equation. But right now, they're kind of, the 4, the coefficient, the 16 coefficients are in the way. So I'm going to, yep, you guessed it, divide both sides by 4 in the first. X minus 2 squared over 4 is going to be cosine squared. And I'm doing the same thing in the second, divide both sides by 16. So you get y minus 2 squared over 16 equals sine squared t. Okay. And now I've isolated this cosine squared plus sine squared. And I can then add both sides using the addition property of equality, if you remember that from back in the day. So what that means is when I add everything on the left together, it's going to equal everything summed or added on the right. So by adding the left pieces, we're going to get x minus 2 squared over 4 plus y minus 2 squared over 16 equals, and on the right we get cosine squared plus sine squared. Yep, you bet it, that's 1. All right, so I can immediately replace what I wanted to in order to eliminate the parameter t, usually for all the problems we've done so far, and probably will do when you have sines and cosines of t's, we end up using this Pythagorean identity to eliminate that parameter t. We just have to build the opportunity to replace sine squared of t plus cosine squared of t equals 1, right? So we work from in this case, cosines and sines to cosine squareds and sine squareds, and then we clear the coefficients in each particular equation, then square. Okay, then replace with the 1 on the right. Okay. Now, what we have here, if you recall, is an ellipse. So the smaller number is the minor axis, although it's really the square root of that. I'm not sure if you remember that. But what we have here is we have x minus h squared plus, in this case, y minus k squared. hk is a center over, now, I forget which one of these is A and which one of these is B. Let's just I'm going to call this the minor axis squared, and I'm going to call the big number in this case, which is 16 is bigger, the major MA squared, axis squared. Right? And so this is the general form. Again, in this case, assuming the 16 is tangled up with a y term, so therefore the major axis is along the y-axis. So what we have here is we have an ellipse with center 2, 2. Oh, we should have done this yesterday, February 2nd, 2022, which also was a Tuesday. And a minor axis, not 4 but 2, in length 2, and a major axis, length not 16 but 4. Okay, and let's see if we can kind of piece that together on the graph. We already graphed it on Desmos, so we're going to go back to Desmos. We need center 2, 2, and a minor axis 2, major axis 4. Let's see if that is the case. Hopefully it will be. Otherwise, we're going to erase this video and start over. And so, yep, here's a center 2, 2. Right, and the major axis goes up 4 and down 4. Right, now the whole length of the axis is 8, but from the center, which is 2, 2, this ellipse works up 4 along the y-axis, works down 4 along the y-axis vertically, and the minor axis is along the x or horizontal axis, has a length of 2, so it brings me out to this point here, which is 4, 2. And then from the center, 2, 2, I'm moving 2 to the left to get to the point 0, 2. Okay, and then if we think direction, right, if I plug in a 0, for x I get 2 plus 2 cosine of 0. Remember, cosine of 0 is 1, so I get 2 plus 2, which is 4. And then the y value, when I plug in a 0, will be 2 plus 4 sine 0, 4 sine 0, 0, so it's just 2. So 4, 2. Here's where it begins, quote unquote, when the parameter t is 0. And then it kind of moves in this direction, counterclockwise. Okay, and I just asked for you to believe that. You can verify that by plugging in nice values of the parameter. Start with maybe 0, pi over 2, pi, 3 pi over 2, 2 pi. And again, we start at 4, 2. We start at this point right here. This is where t equals 0. And it almost certainly works its way up and around till it repeats itself right about here at 2 pi. Okay? So again, this is how we eliminate the parameter. Right, in this case, we end up using the Pythagorean identity. We end up getting an ellipse. Right, and we haven't done ellipses all year. You probably, hopefully remember those from a long time ago. But an ellipse is basically a circle that got hit by a car. It's a major and minor axes are different, right, which is why one axis is it's shorter or stubbier than circles. Okay, so that's how we convert. In this case, we eliminate the parameter, and we can move from here. So guys, let's step it up. Let's go. Good job, and let's finish this winter.